So that brings us to the idea of porosity. Okay, that's your next page of notes. Porosity is the proportion of open space. Porosity is the proportion of open space. And we're going to skip permeability until we get to the next slide, so hold your horses and jump down to the images just below there. Okay, so we're looking here for which of the following have lower porosity and which have higher porosity. So let's take a look. We have clay particles that do not fit tightly together. So take a look at this. Can you see spaces in between these clay particles? Okay, yes. So that has high porosity. Those spaces in between are pore spaces. So if there are a lot of pore spaces, you have a high porosity. What about the one below it? Crystals in granite that fit tightly together. Everything is grown up against one another like a really perfect puzzle. Okay, that one's going to have low porosity because we don't have any pore spaces at all in that case. Then we're going to look at the next one. We have rounded, sorted class that do not fit tightly together. Okay, so you can think of this, they kind of look like gumballs here. So imagine all of the space that's in between those gumballs. Is that going to be high porosity? Does it have a lot of space? Or low porosity, not a lot of space? Right, that's going to be high porosity. If you poured water into that jar, it would fill in all kinds of space there. Okay, in contrast, the one on the right is poorly sorted class that fit more tightly together. So that one is going to have low porosity because a lot of the space that could have been filled by water in the left example, the right example has now been filled in with sand. Okay, so there's less space for it to fill. So well-rounded and well-sorted class, like those in the left jar, are going to have high porosity. Poorly sorted or angular class are going to fit together more tightly. All right, now back up to the top set of questions. What is permeability? Permeability is when pores are connected so fluids flow. When pores are connected so fluids flow. And we're going to look at which of the following have lower permeability and which have higher permeability. Okay, we've got a granite here with many fractures, and we can look at them, they're going in opposite directions, they're connected. So this one's going to be high permeability because those fractures are interconnected. What about this bottom image, compacted clay, which is just shale? Okay, in the previous example, we had uncompacted clay that was just going every which way and had plenty of pore space, but now this has been compressed. So all of those pore spaces have been flattened out. So compacted clay or shale has some of the lowest permeability. Okay, so you're not going to get water that's going to flow through a shale, while it will be able to flow through this granite with many fractures. Okay, what about loosely cemented gravels, meaning they're not held together very well? Okay, because they're not held together very well, that means there's room for movement in between the gravels, so that's high permeability. The next one, porous volcanic rock with separate pores. Okay, so let's look back up at that definition there. The pores are connected so the fluids flow. The easier it is for it to flow, the higher the permeability. The harder it is for it to flow, the less permeability. So if these pores are all separate, they are not connected, that means we're going to have low permeability. We could have, it could have high porosity, right? Many pores, many holes that can hold water, but it will not be able to flow in between those pores. They're just going to be little pockets of water that never moves between them. How and where does groundwater flow? So taking a look at this picture, I want you to describe how groundwater flows. The arrows show the direction of groundwater flow. The water table has a similar shape to the land surface, but is more subdued. So what I mean by that is if you take a look at the left side of this image, that hillside may be at a 45 degree angle. Okay, if that's the case, the water table below it might be at something like a 30 degree angle. Okay, it's going to mirror what the surface looks like, but in a more subtle way, in a less extreme way. That's what I mean by the water table is similar to the land surface, but more subdued. Groundwater flows down the slope of the water table. So just like on the surface, water flows from a higher elevation to a lower elevation down the slope. The same thing goes for groundwater. It's flowing down the slope of the water table. The shape of the water table mostly is independent of rock units, but rock types influence how fast groundwater flows, if at all. So this brings in porosity and permeability, and are we looking at something like solid granite that water can't flow through at all, or are we looking at limestone with big caves, so the water's just rushing through from cavern to cavern? The rock type is going to play a big part in how the water flows. Alright, how does the slope of the water table influence groundwater flow? So we're looking at the same image and just different aspects of the same image. Water moves faster if there's a steeper slope to the water table compared to a more gentle slope. If we're comparing the same kind of material, meaning it's got the same permeability. Okay, so if the rocks have the same permeability, then a steeper slope is always going to mean a faster flow. Okay, just like, again, if you're riding your bike down a hill, the steeper the hill, the faster you're going to be going. Okay, so here we go. We're looking at a steeper slope here on the left. It's faster if the water table is steep, and it's more slow if the water table is gentle. Okay, another thing to point out is the red arrows are showing us the direction of flow, and centering around that stream, we've got water flowing in from the left and water flowing in from the right. So you can have groundwater flow in different directions along a groundwater divide. So this is the same general area, and we've got groundwater flowing in different directions. Okay, it's not always the same. So what other types of things affect flow? We've got porosity. How much water can the rocks there hold? How much can they contain? We've got permeability. How quickly can the water move through there? Okay, we've got slope, which is going to increase or decrease speed based on how steep that surface is. And something like input and output can affect flow as well. If you put in a well here and you're pumping all the water out, then you can change the direction of flow. You can temporarily stop the flow. So rainfall or pumping groundwater can change it as well. And all of this, we're talking about aquifers. So what is an aquifer? I've got this neat little image that's showing us what goes on in Phoenix particularly. because, like I said before, we rely heavily on our aquifer here. So an aquifer is a wet underground layer of water-bearing permeable rock or unconsolidated materials, meaning gravel, sand, or silt, from which groundwater can be usefully extracted using a water well. Okay, so if we take a look at this image, the light tan layer is showing us our aquifer. So where the groundwater is and we can extract it, that is our aquifer. At the top of the groundwater is the water table, and so that's what our zoomed in image is. Okay, because below the water table it's saturated, and above the water table it's unsaturated. And you can see around the water well where we're pumping the water out, we actually change the water table. The water table dips down where we're pumping it out. Okay, and that happens when the aquifer is not being recharged at the same rate it's being withdrawn. Okay, we're not getting the same amount of water put back in that we're drawing out. And we can get several different types of aquifers. We've got a couple different kinds here, but the main ones we're going to look at are on the next slide. So, types of aquifers. We've got an unconfined aquifer, which is open to the Earth's surface and to infiltration. So, when water falls on the surface here, it's going to go through the unsaturated zone and down into the saturated zone. Okay, this is everything we've been talking about so far has been an unconfined aquifer. It's open to the surface. We have a confined aquifer just below the unconfined. So we've got this dark gray layer below the unconfined aquifer. Okay, that's acting as its base. But that base is actually the top for the confined aquifer. Confined aquifer is overlain by less permeable materials. So it acts like a cap on top of that confined aquifer. So what happens here is the confined aquifer is not open to recharge from the surface. It's not open to infiltration. It is confined just to that space between the less permeable materials. Okay, the bottom left image here is showing us a perched aquifer. A perched aquifer is underlain by a low permeability unit. So if you look below what looks like these little boats, which are the perched aquifers, okay, we've got a less permeable unit here, which is the dark gray shale. And so when water percolates through the sediment, it settles on that less permeable shale. So we get a little lens of water. The rest of the water, the rest of groundwater, just keeps on moving through until it hits the water table, which you can see is just below there. An artesian aquifer is where water rises in a pipe on its own to the surface. So what's going on here is we have a confined aquifer that's at an angle. Okay, it's capped at the top, but because it's at an angle, it's being pressurized where it's confined. So on the right side, it's under pressure. It's flowing from the left to the right and building up pressure there. So when you put your well in there, the water comes out all on its own. You don't have to pump it out. So when you get artesian water, that's what you're getting, is this water that was part of a confined aquifer at an angle that was pressurized naturally and able to reach the surface on its own just by putting an opening there and releasing that pressure. Artesian has no implication about water quality or taste. Some artesian wells are salty water, so just because it says artesian, that doesn't mean necessarily it's good drinking water. Alright, that's it for this half of the chapter, and you'll be quizzed on the material up to this point, and you are responsible for reading the first half of the chapter. And everything else is as usual. No homework this week, but the quiz will be posted soon. Good luck!